you all had a chance to read her bio in the description of today's talk. I'll assume you've read it, so I won't repeat it all. I will just say that Danielle teaches computer science at UNC Chapel Hill. She has received many, many awards for best papers. It seems every time she goes to a conference, she wins the best paper award. She was named to Forbes 30 under 30 science list. And here's an award that not even Danielle knows about. It's not in her bio, but at the recent joint statistical meetings that were held in Toronto, her talk was the very favorite of Naomi Robbins. And that's why she was invited here tonight. Danielle, it's all yours.
Thank you so much for the kind introduction. I'm really excited to be here with y'all today. Many thanks especially to Naomi and Cameron for the invite and getting this all set up. So as Naomi mentioned, I'm a computer scientist by training with an emphasis on data visualization and human-computer interaction. So while I draw a lot of inspiration from psychology, which you'll see some of today, I really focus on how can we build tools that allow people to work with data more effectively. So a good chunk of this work falls at the intersection of data science and color, specifically focusing on how we can build actionable, empirically grounded models of the way people reason about data through color, and use these models to drive tools for effective visualization design. And as all too often happens in our field, I think XKCD summarizes my experiences with color the best. Our understanding of color can be as simple as what we see when we open a box of crayons, or as complex as some visual sensation that we still can't perfectly model, even with some of the most complicated tricks that mathematics has thrown our way. This first percept is why some folks write color off as a solved problem, but the second is why pretty much anyone who has really dug into the space sees that we have a lot of work to do to figure out how do we optimally use color in visualization. I got a fitting reminder of this a few months back when my son brought home a worksheet on color mixing from preschool. So as a prompt, this basic sheet got me thinking about all the open challenges with color blending that I often talk about with my PhD students and these interesting minutiae of perceptual models of color. And as I was off mentally in math land, turning this simple worksheet into a research challenge, my son, his littles are so wonderfully up to do, brought me back to reality and proudly showed me his mastery over the true correct solution. It's definitely one of those times I got reminded that a PhD is in part a degree in professional overthinking, but I think this example illustrates the range of ways that we can approach color and visualization. Even something as simple as blending color brings in a wide array of potential solutions, each with its own set of trade-offs. So given this complexity, in my group, we focus on identifying those trade-offs and approaches that allow us to optimize our use of color to represent data. I got started in color through actually a problem in computational biology of all things. So my first project in grad school was to take visualizations of whole genome alignments, which at the time looked something like this, and make them more scalable. So inspired by the brain's abilities to process colors at scale, we eventually used a pixel-oriented approach where we employed color to encode gene scale data and achieved a 10-fold scale up in the number of genomes biologists could work with. And I'm happy to talk about the minutia of what we did in the computational biology space offline if folks are interested, but the real reason that I want to talk about this tool is that this was the point where I kind of tripped and fell down the color rabbit hole. I started exploring preliminary studies that led to conclusions like, while color is bad for things like precise value estimation, the visual system, that's our eyes and brain working together, may differently process color in other visual channels depending on what we're trying to do with those channels. So what does this mean in practice? Well, it makes color really good for other tasks, like trying to assess global structure, especially at scale. And while that initial foray into color started over a decade ago, I now lead a team of amazing students, which you can see here, who are exploring a range of challenges in topics like perceptual modeling for visualization, cognitively accessible visualization, human-machine teaming for data analysis, visualization using augmented reality or computational fabrication techniques, and of course, color and viz, which will be my focus today. So while I have the pleasure of being here to present, the folks that you see here on the screen are the ones who are really leading the work that I will be talking about. So much of this work continues to be on the system side, exploring how we can make data more useful across a range of domains. Color often comes into play in these tools, especially for applications where we need to do things like present overviews of large data sets or direct attention towards important values. However, we see color used in all kinds of visualizations, from scatter plots to surfaces to maps and beyond. But as we discussed in the introduction here, color is hard to do right. Partially, it's because poorly designed color encodings might not just look bad, but they can actually lead to misinterpretation, have even caused papers to be withdrawn from journals like Nature and Science. Work with doctors by Michelle Borkin and her colleagues showed that effective color choices can improve diagnosis rates in arterial visualizations by 30% or more. So good color choice isn't just a matter of being picky about aesthetics, it can literally save lives. But part of why choosing good colors is so hard is that we don't have good guidelines for using color in practice. So here's a set of 17 best practices from a survey by Roxana Bujak and colleagues exploring decades of color use in visualization. Many of these rules are heuristic and they require substantial design expertise to apply effectively. So I'm going to remove the guidelines that fall into this heuristic category and leave only concrete mathematical guidelines. All right, so now that I have these, I'm going to remove those guidelines that are really hard to implement at design time without substantial color science expertise or knowledge of the user that's impossible to obtain a priori because it's unique to individual users or the circumstances under which they're working. And here's our results. So hopefully now you're seeing why color use in visualization is hard. And even if you have the expertise to follow these practices, we've actually found in practice through our own systems and design activities, as well as formal interviews, most designers don't even follow these rules. So let's just dig into one of these here, which is the simple rule of avoid the rainbow. Most folks are probably familiar with the notorious rainbow color map if you've had a chance to dive into popular guidelines for visualization. It's pretty, it was the default for many applications and many years. Users love it and visualization people love to hate on it. It creates misleading boundaries between values, often lacks intuitive ordering, can introduce woefully bad data distortions, and so on and so forth. But people still really like to use it. Well, why is that? Why do we see so many people arguing that the rainbow color map is the best way to represent their data? Well, for one, the artificial grouping created by our brain wanting to lump together all of the red data values and all the blues and the greens and so on may actually help us conduct certain kinds of analyses. So Kari Rita at IUPUI and I ran a study a few years back where we asked people to identify which of 4 data sets comes from a different distribution. So we would show them some set of heat maps like this and say, hey, which one is different? And we tested this task with a bunch of different color map designs, some following best practice, like you see with the blues here, some using color maps that move between 2 hues, like our gray-red, and others which introduce a little more color variation, like the plasma or turbo you see here on the left. Interestingly enough, when we looked at the results, we found that rainbows were actually really good for this task. So you see the 3 rainbow color maps that we tested up in the upper right, where we have the highest overall accuracy. What we also found, however, though, if you look at the x-axis here, is that encodings that provided more nameable colors, think reds, blues, greens, etc., we would have expected to cause us to artificially group our data, but in practice, these actually led to higher performance. So that's not to say rainbows are necessarily good. Like I said, they fall prey to a lot of other perceptual limitations, which I'm happy to chat more about later. But rather it says that there may be a lot of nuance underlying what seems like very simple rules on their face. And I had the pleasure of getting to unpack a wide range of these challenges to this kind of rainbows are bad mindset in a recent computer graphics and applications paper with Maureen Stone and Colin Ware. And while I'm not going to make this talk about rainbows, I talk about rainbows because I think they're very illustrative of where we're at with color in data visualization. Specifically, we have a large range of historical guidelines and practices that are largely unsubstantiated in practice. They draw on traditions from vision science or design practice that provide valuable insight, but we don't yet know how well they work in complex visualizations, which are complex and they contain lots of information, lots of complexity, lots of awesome structure. Further, even with these guidelines, people find using color incredibly difficult and often default to, well, defaults like the notorious jet color map. And that's where a lot of the work on color and visualization research starts to come into play. There's a significant interest in how do we do better and how do we better understand how people reason about color and visualization and use that reasoning to drive new tools and approaches. So returning to my group's work in this space, we really focus on two target questions. The first is constructing models that help us unpack how the visual structure of a visualization changes the ways people perceive data represented using color. The second focuses on how we can use these models to construct guidelines and tools that help people use color better in their visualizations. I've listed some of the relevant papers here if you want to dig into any of this in greater detail. All of these references should be available open access either on arXiv or on my group's website. But I want to start with this first question. How do people see colors in visualization? Well, let's start with the basics. What exactly is color? I've thrown around this term, but it can have many different interpretations. So the visualization community has historically used the CIE lab color space rather than RGB as a space to map data to color. So lab consists of three axes that attempt to mimic the cells in the eye. And we use lab for visualization as, unlike RGB, it is approximately perceptually linear. What this essentially means is that one unit of Euclidean distance more or less corresponds to 1/50% just noticeable difference, or JND. And this JND is important because it's the smallest color difference that people can reliably distinguish at a rate greater than chance. So CIE Lab gives us beautiful one-to-one mapping between our data differences and color differences that is so critical for data analysis. And in practice, it fails absolutely miserably. Let me show you how. So CIE Lab states that we should be able to see 7 different colors in this bar chart. There is no need to adjust your monitors. This expectation simply does not pan out. So visualization designers have hand-tuned color sets for data representation using decades of experience to employ these models as heuristics in crafting better encodings by essentially using intuition. However, even these encodings can start to break down as we change the size of our marks, or even as we change the kinds of visualizations that we're using. So in our visualization encodings, we want to balance discriminability, which is the ability to preserve important data differences, with the range of desired data differences we want our visualization to express. So to achieve this goal, we created a data-driven method to proactively anticipate how color difference perceptions change as a function of the visualizations we use. That is, we wanted to try to create models that allow us to match the data differences we see in colors to the differences that truly exist in our data. We developed 3 different models using this approach, the first focusing on what we call diagonally symmetric marks, like points in a scatter plot, the second on elongated marks, like those in bar charts, and the third on asymmetric elongated marks, like we see in a line graph. In total, across all our experiments, we collected over 34,000 data points to see these models across a range of crowdsourced viewers to account for a range of individual differences in people's perception, people's experiences, the environment, and the devices they're using to view these graphs. For the sake of time, I'm not going to dive into the nitty-gritty of these methods, but I am more than happy to chat about the details of these experiments offline. However, I do want to touch on what it is precisely we found. These studies show that our abilities to perceive differences in data encoded by color vary according to the design of a visualization. These abilities vary systematically by mark size and by shape. Our ability to distinguish marks improves as both the data points get longer and as they get larger. We also found that these gains are asymptotic with respect to elongation, but they can be quite dramatic. So our visualization dependent models predicted that we lose about 70% of our data differences by just using CIA Lab alone, like we saw in that first bar chart. But by considering the geometries of a data point, we can buy back about 30% of that difference, meaning we can resolve differences a lot more reliably if we choose colors based on our visualization design. The really cool bit with these results is just how cleanly we can make these predictions. We can actually compute normalizing constants using the range of allowable mark sizes that feed into our Euclidean distance formulation to predict with a fairly high degree of precision how well people will be able to discern color-coded data in a given visualization. So we have these models. What do we do with them? Well, one of the ways we can use them is to evaluate our own visualization practices and understand where current design approaches may fall short. You'll recall that designers hand adjust for the shortcomings of CIE Lab. Most colors in visualization research and many common tools comes from a tool called Color Brewer. Color Brewer offers a series of hand-designed ramps that are considered a gold standard set of encodings you can choose from. It has been an absolutely invaluable tool for helping people make better color choices, but these colors are primarily designed for use on maps. We can use our empirical models to predict the effectiveness of an encoding like one from Color Brewer on charts based on known minimum parameters of our visualization. For example, imagine that we have scatter plots with 10 pixel wide points and line graphs with 4 pixel thick lines, which are the standard on Tableau on a 15-inch laptop. We can use our models to anticipate which of our 9-step Brewer sequential encodings will be robust to these charts. That is, which will allow us to distinguish between each of our 9 categories and which will create ambiguities in the data. Using our model, we found that 13 of the 18 Brewer encodings actually failed to preserve sufficient color differences for these visualizations. So this finding suggests the need to consider mark-aware models in encoding design. We're actually losing much of the fidelity that we assume even in expert-crafted designs due to assumptions about discriminability embedded in these conventional models. And this becomes a big problem. It suggests that we need to rethink to some degree the way that we craft ramps. So this particular project really focused on the idea of shape and size of mark and how they influence the way we perceive data using color. But some of our more recent work actually shows that the distribution of data itself may play a role. For example, traditional guidance says that people will be able to reliably infer that darker quantities in a color map represent higher values. This is called the dark is more bias. So in the figure on the left, people will think that the left side has higher measures on average than that of the right. We've got some upcoming work at Viz in collaboration with Karen Schloss's lab at Wisconsin that shows that shifting either the distribution or granularity of the data, like you see in the examples on the right here, can actually change what values people perceive as higher depending on different properties of the color map. I'm not going to unpack these charts, as if I'm being honest, we're still unpacking what they mean ourselves. But this provides some preliminary evidence that the spatial distribution of data may also affect data interpretation in color encodings. And while these models have focused on color map to continuous numeric color quantities, we see similar changes when we start to think about the robustness in categorical colors. So here we can probably readily discriminate between the 3 categories of colors in the scatter plot. We see this kind of gold, kind of brown, kind of green. But once we scale up to 6 or even 9 categories, trying to attend to each individual group feels really tricky. So conventional wisdom says that we shouldn't encode more than 6 categories using color. Well, it turns out that even though this problem feels hard, people are actually quite good at making sense of individual categories using color, even beyond 6 categories. We conducted an experiment where we showed people scatter plots like these with anywhere from 2 to 10 different categories and asked them which category was the highest on average. And although anecdotally, folks found this task really hard, you can see from the graphs here that for most of these color palettes, people were still really good at this task, even with 10 categories. So each graph here represents performance with one handcrafted expert palette, with accuracy on the y-axis here and comparing means, and the number of categories shown on the x-axis. And while robustness certainly varied across these palettes, this study suggests that that rule of thumb about no more than 5 to 6 categories doesn't hold in practice, at least objectively. So that's a whole lot about visual perception, but as I mentioned at the start of this talk, I'm a computer scientist by training, and so turning around and making these findings useful and embedding them in tools is near and dear to me. So I want to talk a little bit about how exactly do we make these results actionable? Well, one approach we can use is to apply these models to proactively fix encoding challenges and encourage more effective color use in visualization, support experimentation, even conduct post-hoc correction. For example, if we have the red to blue color map that we see here, we may lose important data differences as our data points shrink due to factors like added data or smaller displays. We can use our models to anticipate when this will happen and push apart the ends of our encodings, and then reinterpolate the encoding to preserve that perceptual uniformity. Similarly, if our visualizations start to change, we can use our metrics to pull the colors together to make better use of the available encoding space and allow more wiggle room for aesthetic choice. While tools like Color Brewer have been instrumental in providing color agency in visualization, though, this choose your favorite encoding style of approach means that if there's not a ramp that matches your target parameters, you're kind of out of luck. And we also see some of the fallout of this predefined, pre-selected, handcrafted set of palettes when we look across larger numbers of tools. So what we found is that actually there's a little bit of deja vu when we start to look at representations even within the visualization research community. So here I have a set of visualizations that I pulled from one track of proceedings at the top visual analytics conference. And you can see we use these color encodings a lot and maybe rely a bit more heavily than we realize on predefined canned ramps like those created by Color Brewer and others. In fact, we found in our analysis of those proceedings, 25% of papers from that track contain at least one viz with one of these red to blue ramps. And this might be problematic if we're causing our visualizations to blend in with the crowd. There are situations also where we need unique colors. For example, if we're working on branded presentations, we may need to use the colors associated with that brand. But there isn't exactly a ton of demand for a lift pink ramp. So what do we do? Well, this challenge led us to what we've tackled in this next work, which I want to show you, which is how do we actually create effective color ramps? So we developed an algorithm that lets you create high quality ramps using single guiding color. Let's start with the Skype blue that we see here. We can create a map by computing characteristic structures in designer ramps that they form as they traverse a perceptual color space. And we can apply these curves to a given color, say our Skype blue, to generate a set of ramps with different visual characteristics that developers can then select from and refine. So our approach uses a concept called design mining, which is essentially where we use data mining to model and reproduce common design practices. So we use design mining to try to capture the properties of effective color use in visualization. Our algorithm relies on the fundamental observation that ramps are just curves constructed through a 3D space. So we assert that the structure of this curve controls the aesthetic appearance of a set of colors, and the ways we sample data points along the curve control the perceptual properties of a ramp. So these curves in practice that I'm going to show you actually traverse a 3D CIE lab volume. But if I try to show you that on this 2D display, it gets a little tricky to try and disentangle. So I'm going to show them as projected 2D curves. One in the hue space, so think about this as on our A-axis we have the amount of red or green, and our B-axis we have the amount of blue and yellow. And the second of these in terms of lightness and chroma. So this is going to be how light or dark do we have our colors and how saturated are our colors. So our algorithm consists of 6 steps, roughly categorized into 3 phases. The first two steps create a uniform training corpus, which we can use to derive our models. The second 2 cluster these curves based on their structural properties and compute characteristic structures describing each color. The final pair take these clusters from an abstract space and anchor them in color space to generate an encoding. I'm going to walk through each of these steps at a very high level here, but I'm happy to dive into more details after the talk. We've assembled a corpus of 222 handcrafted color ramps from known sources in the visualization community, including Color Lovers, Tableau, R, and Color Brewer, which we use to ground our models. We normalize each of these color maps by treating the colors in the ramp as a control point and fitting interpolated B-splines to these points. Once we've constructed these structures using this interpolation, we use arc length interpolation on each of the curves to resample the curves to a uniform number of points along roughly equidistant intervals in CIA lab. So the result is that we should have roughly a uniform perceived difference between each of these control points in practice. We clustered the normalized curves according to their physical structures. So here we see a 2D projection of these plots with the original curves shown in gray. The basic idea is that we can align curves by moving, rotating, and reflecting them to minimize the overall distance between control points. We then use either a k-means clustering based on structural features of each curve or a Bayesian clustering algorithm applied to an elastic shape descriptor to group curves sharing similar structures. Once we've done that, we compute a characteristic curve by identifying the mean structure from the full set of clustered curves. And while there's a lot of math underlying this process, as you can see from the projected plots, most of our curves are actually far from the linear and uniform structures recommended by most design heuristics or design tools that allow you to do something like pick two colors in CIA lab space and interpolate between them. It's a fairly common practice in a lot of color map creation tools. These curves instead that are created by experts kind of wiggle all over the place in interesting ways that create subtle but very critical affective shifts. So once we've constructed these kind of nice wiggly structural curves, we have a characteristic curve that we can apply to generate our color map by adjusting that curve according to the relative lightness distribution of the underlying structures. So what does this mean? Well, basically we start with the curve position according to the mean model lightness for a given curve cluster. We then find the point in the curve closest to our desired color, let's say our sky blue in this case, and then we shift the ramp such that we minimize lightness variation from our original model and anchor the resulting map in color space to get a new color ramp. People can then rotate, scale, and translate the curves to tune them to their liking. So we tested our approach in 3 different ways, including replication and stress testing with poor colors. But we also conducted an experiment with expert designers using color maps in different visualizations to assess accuracy and aesthetics. This experiment compares objective and subjective performance between the encodings generated using our approach, those generated using linear interpolation, as in many popular design tools, and those handcrafted by designers and sampled from our training corpus. So to go into a little bit more detail about this experiment, just to give you some context for our results, we start off with 25 ramps pseudo-randomly seeded from colors from our designer corpus. So these use 2 different clustering approaches that we built into our tool. And these serve as kind of our target examples of our system performance. We compared these encodings with with a set from 2 different baseline conditions. The first of these is linear interpolation. So basically we choose 2 colors at random from our set of designer color maps. And we make sure those 2 colors are at least 40 units apart in lightness based on existing expert heuristics. Then we linearly interpolate between those colors in our CIA lab color space. We also used a designer baseline to serve as our gold standard, where we just chose at random 25 ramps from our designer corpus. And this baseline gives us a theoretical threshold for what a gold standard ramp should look like. We then showed people 3 different visualization types: scatterplots, heat maps, and choropleth maps. And we asked 35 designers from around the world to complete the study with an average of 6.2 years of self-reported professional design experience. And what we asked these designers to do was essentially provide us with 2 data points per graph. So the first one was trying to simply just read a value. If I give you a particular visualization, can you find the point that corresponds to a given value in that color map? And the second was to rate their subjective preference for the color map itself, which we actually just summarized as being as simple as, how pleasant is this color map? So we got both objective performance and subjective preference measures. When we actually look at this data, we can kind of categorize our results according to our perceptual objective measures and our subjective aesthetic measures. To just cut to the chase here, our approach worked. In these graphs, Our approach is shown in green, and our baselines are in blue. So for our perceptual measures, we found that participants were more accurate with our approach than with linear ramps, and trended towards being more accurate with our approach than even the handcrafted designer ramps, but this difference was not statistically significant. We found the same pattern with aesthetics. Designers preferred our approach to linearly interpolated ramps and found our models at least as aesthetically pleasant as designer ramps. The takeaway here is that for these visualizations, an expert participant pool found the ramps generated using our approach comparable to those handcrafted by experts. So we took this as a good sign that our algorithm was doing what we hoped it would, and we embedded these models in a color encoding design tool called Color Crafter that provides a front end for this algorithm. So with this tool, you can specify a target color to generate a series of ramps. You can then manipulate these ramps using a sequence of affine transforms, including translation, rotation, scaling, and reflection along various axes of color space. These transformation-based edits allow you to quickly customize the encoding without sacrificing the quality of the resulting ramp. Through this approach, even novice visualization designers and developers can rapidly create custom color maps that embody best practices in visualization design using as little as just one guiding color. And for fun, we can see an example of what this approach allows here. I seeded a set of ramps using Carolina Blue. And if it advances, there we go, here are the results. So by inputting the target color into the tool, what you can see is we can generate a series of color encodings that adhere to our target color, but give us a little bit of a mix of different ways that we could represent that data. And so while this tool is really a lot of fun to work with and to build, we actually have a tool that is under review right now that I'm super excited about, because what it's done is it's actually used reinforcement-based learning to take the same specify one color and enable people to express their preferences for a given target visualization using just pairwise preference selection. So the basic idea here, you put in your visualization, the color map gets applied, and you ask designers just simply to choose what's your favorite about a dozen times, and you pretty reliably can get high quality color maps generated on the fly from this approach. So stay tuned for more details about that. I'm really excited to release it, but like I said, we're currently under review on this particular project. So just to wrap up here, my group is really focused on these two driving questions to understand how can we use color more effectively in data visualization, focusing on how people perceive color and how we can model patterns in this perception to try to build more accessible design tools. That said, there are still a lot of things we need to figure out. I stand by my opening argument that color is far from a solved problem. I want to close with some of the most pressing open questions that I see from my perspective in hopes that this might seed some conversations moving into the future. Note that I'm a little biased here as we've got some ongoing work trying to tackle specific aspects of these. But I think there's a lot of open opportunities in thinking about how do we look at the interplay between the design of a visualization and the colors that are more effective for it. We've seen some evidence that data distribution matters, that shape matters, that size matters. There's also things like proximity, viewing environment, data semantics that might come into play and that we need to figure out how to support more fluidly in color use and design. We're also really curious about how do we enable a wider range of designers and users to work with color more effectively. One of the really cool things with the Color Crafter project is that one of the developers on that system actually had color vision deficiencies, but was still able to produce professional quality color maps despite having these color vision deficiencies. So I think there is a real opportunity to look at how do we support novices, experts, people with varying abilities in actually engaging color more effectively. And with that said, I'm really curious about how we might do this intelligently. Does this always have to be done in design time, or does it make sense to actually have visualizations and color choices in visualization in particular that can adapt to different circumstances and different needs and capabilities of individual users or individual data sets? So with that, I would like to wrap up and thank you all for listening. Thank Naomi and Cameron again for having me here today. And I'm looking forward to the discussion that continues either here or feel free to shoot me an email offline, and I'm always happy to make some time to chat.
Thank you so much, Danielle. I wish we had the clapping feature enabled in this webinar account, but we don't. But There was enthusiastic comments throughout your presentation. People are very stoked about the animations that they were seeing, the specifics of the work that you were presenting. I'm stalling for time a little bit so that you have time to drink water, compose yourself, because that was a lot for people to take in. But I'm just going to take a moment to encourage people to put their thanks in the chat, their questions in the Q&A box. And I think Naomi is going to kick us off with a
Okay.
reaction.
We want you to write your questions, as Cameron said, in the Q&A box. But while we're waiting for that, I'm going to ask and answer the question we always get, no matter how many times we answer it. And that is, will this session be recorded? The answer is yes, it is being recorded. My policy is, after Cameron sends it to me, I sometimes chop off the beginning or end if there's dead time. I then send it to the speaker to look at. We've had speakers who did not want it publicized. Their attitude was, if people want to hear it, let them hire me. But Danielle has said she's quite open. The next question is, how do I access it? Once we get Danielle's permission to post it, I will put the link in the comment. If you go to our webpage, you go to this presentation, there's room for comments. I will put the link in the comments. Expect it will take about a week before Cameron gets it to me, I edit it, I get it to Danielle, etc. But in a week or two, if it is posted, you will get the link in the comments to this talk. Now, I still just see one question here, which is amazing presentation. Is there any advice for designers what to follow or avoid in visualization? It's amazing understanding the why behind everything, but is there something I can use in my day-to-day? Thank you and congrats.
Yeah, thank you all again for the feedback, and I'm really glad you enjoyed the presentation. I think that how do we make this actionable is really important. So things that I would say right off the bat for just day-to-day color use. One is actually like avoid the rainbow. I talked about some limitations where it turns into being somewhat problematic. There are also things like it's not very accessible if you have viewers who have a color vision deficiency, which is a good chunk of people, actually. I think it's, depending on what statistics you're looking at, anywhere from about 7 to 10% of the population, many of whom don't quite realize it. And so, you know, that's always one good one to avoid. The other thing, the thing that I would encourage folks to focus on most directly is to, and actually I'm going to stop share here, is to really think about, what does your color map look like on your visualization, right? So many of these models that we've constructed come from the fact that folks would apply these ideas, they would apply these guidelines, they put them on their viz, they wouldn't work, and they say, well, where do I go from here? And so I think one of the most important things that you can do when you're working with color and viz is put them on your visualization and then ask yourself, can I see the differences that my users need to be able to see? If you need to, for example, communicate ideas around averages or around variance, can you make those estimates? If you need to distinguish different categories, can you distinguish those categories? There are some guidelines that hold in practice quite well. Things like use light to dark color maps if you have continuous numeric data. Use what's called a diverging color map, where you go from one color to a neutral to another color. So if you think of a lot of the climate visualizations where we go blue to white to red, those are really good if you have continuous data with a 0 point in the middle. Things like rainbows or categorical palettes are really good if you have categories. But those kinds of rules of thumb are very loose rules of thumb in practice. And really, it's all about, does your representation show you the thing that it needs to be able to? And you often don't know that until you actually look at the color on your target data and your target design.
Okay, the next question is just wanted to make sure I understand the tool you demoed that allows you to pick a color and then use the tool to rotate and stretch the color distribution is still in development, yes? Where would we be able to see it and when might it be available?
Well, I'm happy to share the link. So it is mostly fleshed out. It is very much a research tool. So I think the UI is not necessarily at a professional level, but it is available for folks to experiment with and play with. The tool itself is called Color Crafter. It is hosted on our lab's website. And I can post a link in the chat or share a link after the fact with Naomi and Cameron if that's helpful to the system itself. I don't unfortunately have it handy because it's linked off of our lab website, but that is available to experiment with.
I would put it in the comments section. After your description of the talk, there are comments, and that is permanent where the chat is not.
Great.
Your remarks that mark type and dimension affect the effectiveness of color scales really landed for me as a business intelligence professional. I've observed the same. Oh, question coming. So we have to wait for the question. Any other questions, please?
I'm going to mention one. Somehow as a host, I cannot use the question box. I was really curious about the corpus of labeled palettes that you are working with for your training data.
Yeah.
You mentioned a number of tools that are used for people programmatically generating graphs like Tableau and R. I'm curious if you had the chance to find palettes from non-programming sources, or I'm thinking about people hand picking palettes in data journalism or other places as you're building this.
Yeah, so at the time we were really focused on crawling existing repos of very large color maps, because what we were seeing is that those color maps were more or less indicative of the kinds of things that we would see in practice. And they had a little bit of additional validation in that they had made it into these tools. So they had been curated not only by the experts, but also by the people developing these systems who are somewhat aware of the best practices, even if they're not necessarily specifically color researchers. But it's really an interesting question. We did not look more broadly into other kinds of data journalism sources. Color Lovers is kind of an interesting community because it's not necessarily explicitly tailored to visualization. So someone can come in and design, a one-off representation that they use for a particular application and upload it to the site. We actually had to do a little manual curation of some of the Color Lovers examples because some of them did violate best practice. But, it'd be really cool to see. And I think at the time, I will say computer vision wasn't to a spot where we could easily do that. But I think now there definitely is an opportunity to potentially go in and create something that could scrape out the palettes from a number of different kind of bespoke visualizations that have been created for specific purposes. And it could be really cool to see some of the analysis. And that might be one way, for example, to start to pull in data semantics and other things like that we haven't accounted for in our current tools. So TLDR, we haven't really done it, but it'd be really cool to see.
Seems like it could be quite a project for people to have to hand extract it from, because it's not programmatically encoded.
Yeah, there is some interesting work going on right now. Both Manish Agrawala's lab and Jeff Harris' lab in the past have worked on systems for trying to extract palettes from visualizations. So that might be one place to start, but I don't know.
Thank you for that. Yeah, I really enjoyed seeing how you incorporated both performance and aesthetic metrics at the same time, because that's a tricky thing for people with palettes.
Thank you.
It looks like Mark has finished typing his question. I'm going to continue with it if it's all right, Naomi.
Certainly.
So Mark noticed that some hand tuning has to be done to overcome redundant encodings, for example, using line thickness or shading in addition to color. And he's curious, I guess the question is about using encodings in addition to color to do some of the hand tuning. What you think about that, or if it's been studied as well.
So the truth is it's pretty messy. So one paper I did not talk about, we started to look at a variety of different shape representations. So for example, if I used a filled circle versus an open circle, if I use short dashes, long dashes, squares, triangles, asterisks, I think we tested about 20 different shapes in total and applied the same methodology, trying to look at like, how do our color models vary when we start to experiment with some more of these factors and use some of these redundant codings? And the truth be told, we found that it matters. And that's about as far as we were able to get. There was no necessary systematic variation that we saw as a function of any sort of shape parameters that we were able to ascertain. You know, it's quite possible we overlooked something. But truth be told, I think this is where, like you said, that manual tweaking starts to come into play. You can use these models as a fairly reliable benchmark. We found that while there was a significant variation introduced by shape, none of it ended up degrading that pattern that we saw of very much an asymptotic kind of behavior, of that kind of inverse model of as things get smaller, they proportionally get more or less discriminable. So what it ends up being, I think, is you can use these kinds of models to give you a first order approximation of how things are going to change. But if you really want to get into those fine-grained details, especially with redundant encoding, a lot of that is going to come down to individual tweaking. We have some models available for computing how that difference might work for very common shapes that we see in a lot of shape palettes in popular design tools. But truth be told, I think this is one of those places where human perception gets really messy, and we don't necessarily have great models for how we can extract all of those different details and differences.
Thank you. So next we have a question from Carolina, who opened with a wonderful talk. Thank you so much. Is there a resource you can recommend that succinctly lists the issues with rainbow color palettes?
So that's a great question. So in the paper that Colin, Maureen and I wrote, oh goodness, when did that appear? I think back in April. There was some discussion of what the big issues are and what we do and don't understand about those big issues. But there's also a fantastic, so there's the canonical paper that's called Rainbow Color Maps Considered Harmful by David Borland that lists out a number of these issues in detail. There was a follow-up work that was done. I think it also came out last year by some folks in the geosciences. Arzu, and I am blanking on her last name at this point, I apologize, but they were doing some fantastic work where they did a large-scale survey of all of the work that had been done on the rainbow color map. And so I would say both of those, I believe, are available open access and would be fantastic resources to start with.
We will definitely track those down and put them in the comments for afterwards.
Thank you.
Rebecca is wondering about expanding the tool to include more than one inputted color to generate palettes.
Yeah, so we did spend some time thinking about, would it be helpful to provide a second color to kind of give a directional trajectory, right? I talked a little bit about how you can rotate these color palettes in place to change the color composition of the palette. What ends up being really tricky there is that since these palettes are nonlinear, you can't necessarily rotate them and scale them effectively and preserve the color relationship between different points. So in other words, if I use two different colors, I might actually have to really change the overall geometry of that curve in order to interpolate those two colors using the curve. So that's why we stuck with one color in practice, largely to kind of simplify things and to avoid shifting the underlying geometry of the structures. That said, one of the things we also found with this tool is that being able to give more control over the kinds of colors that are being generated is something that people do desire, especially if they have more expertise. Like I handed this tool off to a good collaborator of mine who is a professional artist. And she's like, I want to do more with this. I want to do more than just wiggle it around in space. I want control over things. So I think there is, you know, a space and a spectrum of interactions in the color design space that need to be explored to figure out how do we support someone who is an absolute novice. Let's say it's somebody who has data, knows they need to build a visualization and doesn't quite know where to start with it, versus someone who has decades of design experience. And then there's everybody in between, which is probably the vast majority of people who are trying to design these color maps. So kind of to build and expand on your question a little bit here, I think there are really interesting challenges and really interesting open concepts around what are the best design workflows out there for constructing color maps that we don't necessarily have great guidance on yet.
Thinking about your answer on perturbing the thing that comes from the model, I had seen a presentation some time ago about people programmatically defining drone flight paths. You have a photographer who has some waypoints that they want to hit, and they use the machine to find something that is physically possible, but doesn't necessarily look good when you actually fly it. And so they also had to work closely with artists who wanted to perturb the initial thing slightly, and still found this nicer than hand tuning every single point in the flight path. It feels like another space where there's this mix of a quantitative and an aesthetic concern that you're trying to balance in the tool.
Exactly. And, the overly honest truth is when I started doing work in this space, I thought this would be as simple as help people find two good colors and linearly interpolate between them. I was quickly proven wrong. And that's when I started collaborating with Maureen Stone up at Tableau, who was able to kind of walk me through more of the fact that, like, hey, maybe these perceptual rules on their face don't do what you actually need them to do. And I think when I had that moment, it kind of blew my mind as a grad student of, oh, okay, I have a totally different conception of what's actually going on here. So I hadn't heard about the drone paths. That's fascinating. It makes a lot of sense, though.
We have another question from Joyce Robbins about she's interested in whether you've had the chance to study potential cultural differences in color perception.
So my team has not. I do know that there are folks out there who are working on this problem space because, like I said, individual differences with people end up being a huge part of this, even in how people interpret color, right? For example, in the States, we have a lot of maps in political season that are red and blue. That color semantic is actually inverted in certain countries in terms of liberal versus conservative parties. If you were to invert those in the States, we would all get horridly confused, and most people would probably completely incorrectly read visualization. But there's also different interpretations of what's good and what's bad, and also different preference-based kinds of expressions, right? Different cultures tend to gravitate towards certain color palettes, speaking in broad strokes, obviously there. But it's one of those where there is some really cool work going on. We haven't, unfortunately, yet had a chance to get into it, but it's one of the reasons I'm really excited about some of the preference-based stuff that my student Matt Hong has been working on, about thinking about, how is preference expressed and how might we capture it effectively in different tools.
It seems like a whole, you could have a whole lab just about the cultural perception part of color.
It's true. And it's so important, especially as, we move to this more global communication through data, and making sure we don't commit color faux pas is important and hard.
The polarity point is very interesting because we maintain a data or a dashboarding tool within Datadog, and people have the opportunity to define whether positive should be interpreted as good or bad, like positive or negative numbers.
Yeah.
And that will flip the colors to try and accommodate that sort of a cultural preference for whether an alert should be red or something else.
Awesome. That's fantastic. Yeah. User-centered approach seems like a really good one for that.
I have one additional question that I will share, but we've gone through the stuff from the audience, so it will probably be the closing question unless another one comes in. So with the different colors that were picked here, we were mostly talking about quantitative color palettes from what I could tell. I'm curious if you're how often your work also talks about categorical color palettes. So you're not trying to read the number out, but just pull the category out of a visualization.
Yeah, so we have done a little bit of work in categorical palettes, and largely what we've studied is just how do we scale them, right? When we think about these kinds of heuristic rules of thumb of no more than 5 or 6 colors can be distinguished at any given time, is that true? Can we distinguish more categories? We've largely fallen to expert analysis because truth be told, there aren't a lot of great heuristics for designing categorical color palettes other than make it so that the colors are different. Different designers have their own preferences for how they do this and how they manipulate hue and lightness to try to emphasize different categories. But in truth, I think it's a very open area. I think the most thorough work that I've seen in this space is actually a tool called Colorgorical. So Colorgorical was developed by Karen Sloss's group out of Wisconsin. And what they do is they essentially heuristically select a whole bunch of random subsets of candidate colors given a set of user expressions. So let's say, I want in this hue range, I want this number of colors, I want to make sure they're this different. And then there are different metrics that you can tune and you can weight to say, all right, I especially want to preserve perceptual differences, or I especially want to make sure I have differently named colors, or I want to make sure different pairs of colors go really well together. And you can kind of adjust the weight of these different metrics. And what the system will do is it will go in and it will evaluate these candidate palettes based on the weightings of the metrics that you present and give you what the top candidate choice is. So it's a very kind of stochastic process, a well-guided stochastic process. But in terms of more of a generative style of how do we help people design categorical color palettes, I think there's still a lot of work to be done. Yeah.
I really resonated with the example in your slides of showing the need for people to use certain brand colors for certain series. And there were some mentions in the chat of other people relating to needing to represent brand colors for marquee groups as well.
Yeah.
Thank you for the pointer to Colorgorical.
Yes, and I apologize if I'm reading the chat right. That link might be broken because I'm in the process of migrating my lab's website from CU, the University of Colorado, to the University of North Carolina. Long overdue migration, and I haven't had a chance to debug all the links yet. So it's possible that if you replace that UNC with a CU, that link might work. But famous last words. So,
Are there any other questions? Then I wish to really thank you. If you look at the comments, you will see how well received this talk was. As Cameron said, we wish we had a clap function, but I see some people put claps in the chat. And I thank everybody for coming. I certainly thank Danielle for speaking, to Cameron for hosting, and we look forward to seeing you all again.
thank you, everyone.
Naomi, did you want to?
This says the CU redirect to UNC, which is still broken.
All right, I will have to go in and fix that tomorrow then. Thank you for the heads up there.
All right. Thank you everyone for attending. I'm going to end the recording